Okay, let's continue where we left off last time. With organic chemistry.
Organic chemistry is going to be on the touch.
Yes.
Are we going to go over the rule questions at the end of our Tuesday?
Yes, but we're not going to do it today because I want to make sure to get stuff ready for the test. Lab from Tuesday is not due for 2 weeks because next week's the exam. So we'll look at that next week, Thursday, yeah, because I don't want to confuse anybody before the exam. So we'll do it after the exam. But if I forget next Thursday, can you remind me again or somebody? Thanks. All right, let's look at these molecules. So what we talk about now, this will be kind of the last stuff that you'll see on the exam. We talked about these alkanes, and we started looking at these condensed and line structures. So we're going to get into that a little bit more and get a little bit more complicated with it today. So let's start by thinking about these line structures. This is really important because we're going to use these for pretty much exclusively for the rest of the semester when we talk about these molecules. It's just, especially as the molecules get big, it's too cumbersome and annoying to write out every single atom every time. So we got to get good at line structures because they're so much faster and easier to write. They're a really good way of communicating structural information. So just to remind you, we looked at this molecule. Let's just pick one. We'll pick butane. And there were a few different ways we could write it. We could write it like this, which we called the Lewis structure. We can write it like this, which is the condensed structure. There's actually another way to write a condensed structure where you keep the hydrogens condensed, but you still write lines between the carbons like this. That's sometimes helpful when we have a structure that's kind of like branching and doing weird stuff. And then we have this line structure. And at the end, I asked you, can you try to figure out what's going on with those line structures? And somebody said, yeah, it has something to do with how when the line bends, there's carbons. And that's exactly right. So if we add numbers to these carbons, just to count them and keep track of everything, butane has 4 carbons and 10 hydrogens. And those 4 carbons are shown in the line structure by being either at the ends or at the intersections of lines. So there's 3 rules for line structures. 1, we assume that there are carbon at the ends and the intersections of lines. So whenever we've got an end of a line or whenever 2 lines come together and either make a point or a cross or anything like that, that's where a carbon atom is. So we don't draw out the carbon atoms. We just draw these zigzag lines. Second, let's deal with the hydrogens. So how do we know how many hydrogens there are and where they are if all we have is these lines? Is there a way to predict that? I mean, there is a way to predict it. Can you see what it is? What is it? But how do you know that? By looking at the structure? You're right. I mean, that's always going to basically be the case, but there's a reason for it. And the reason is carbon always has 4 bonds. We talked about that before, right? That's so predictable, and that happens so exclusively that we can actually just assume that there's always enough hydrogens to make 4 bonds for every carbon. So when we look at this right here, we can say, okay, well, that already has 1 connection shown, so it must have 3 more because it's got to have 4 total. So we know there's got to be 3 hydrogens there because 4 bonds total, 1 of them's shown, there's got to be 3 more. If we look at the next one, same idea. Here's our carbon. 2 bonds are shown, so there must be 2 more there to make 4 because we've always got to have 4 bonds. So, oops. We can assume that there are enough hydrogens well, let's say so that each carbon has 4 bonds. So let me draw you a slightly more complex line structure, and let's go through it and figure out how many hydrogens are on each position and actually figure out the molecular formula of this structure. I'm going to draw it kind of big, and it's going to be a little weird, but that's okay. So we've got this kind of ring structure that connects all around, has a double bond in it, and then another thing coming off there. So let's go through and calculate the number of carbons first, and then we'll look at the number of hydrogens on each carbon. So based on rule number 1 here, how many carbons are in that structure? Seven, right. So you got a hexagon which has 6 points, and then you got the 1 more coming out there. So 1, 2, 3, 4, 5, 6, 7. Every time the lines come together or there's an end of a line, we count that as a carbon. We've got 7 carbons. Let's figure out how many hydrogens we have. Yeah, Lindsay. Yes, that is a double bond. So that's saying that those 2 carbons are double bonded together. They share 2 pairs of electrons instead of just 1. So right here, yeah. Okay, let's look at the hydrogens. So what we do when we figure out the hydrogens is go around each carbon and determine how many hydrogens are on that carbon based on how many it would take to get up to 4 bonds. So we'll start off on the end over on the right here. This one has 1. No, it would not be 18.
15, 16.
Well, let's count it out and see. You're all wrong so far. Can we just count it out? Okay. So let's look at that very end one. So the one on the end has 1 bond shown, which means how many more hydrogens does just that carbon need? 3. So we've got 3 hydrogens right there. Everybody see that? Because that carbon needs 4 bonds, so that means we need 3 more. Okay, next carbon over. How many there?
2.
Why 2? Well, each carbon needs how many bonds? 4. And how many are shown? 4. Everybody see the 4? If we're looking at this carbon right here, 1, 2, 3, 4, because it's a double bond. 1, 2, 3, 4. So that carbon has 4 bonds, which means no hydrogens. So no hydrogens there. All right, let's move over to this one. How many connections does this one have? Everybody see the 3? 1 here, 2, 3, because the double bond counts as 2. So how many hydrogens have to be there? 1. There's got to be 1 hydrogen coming off that carbon.
Can you do that one more time?
Yep. So each carbon needs 4. We've got 1, 2, 3. So we need one more hydrogen to make 4. Okay, keep going that direction, clockwise. What about this one? How many hydrogens need to be there? 2, right, because there's 2 bonds shown. So that means we need 2 more hydrogens to make 4. Next one. 2, good. Next one. Also 2. And the last one. Still 2. So we count all those up. And we get 12. For the formula of this molecule is C7H12. Yeah. Every carbon has to have 4 total bonds. So if one of them is the carbon-carbon bond here, that means it needs 3 more hydrogens to get to 4. Yeah, the black line is the connection to the next hydrogen, or the next carbon there. Okay, let's try it again. Hold on a minute. All right, that's also a double bond there. It's hard to write it on the screen. A double bond. Okay, find the formula of that molecule. It has 2 double bonds, yes. What do you mean?
Like for the one on the left,
Mm-hmm.
we did 7, but you didn't count the double bond.
Right, so the double bonds are between carbons. So we would say there's a double bond between this carbon and this carbon. And you're right, we wouldn't count those as extra more carbons. It just tells you how, because the number of bonds tells you the number of pairs of electrons that they're sharing. And so that just says these 2 carbons are sharing 2 pairs of electrons instead of 1. Another way to think about that is molecules always have to be continuous, like all the atoms are connected to each other. So if you have a random line out here somewhere, those wouldn't then be connected to the other ones. Okay. So everybody try to count that out. Number of carbons, number of hydrogens, so you get a molecular formula. All right, we got one? So let's count them out together. Carbons, I've got 1, 2, 3, 4, 5, 6, 7. You get 7 carbons again? Okay, and for hydrogens, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10? All right, great. Good job. All right, the third rule, and third and last rule of line structures, now that we know about the carbons and the hydrogen, is what about all the other stuff that could be there? And this one's pretty easy. Other atoms, like oxygen, nitrogen, whatever, are not changed And their connected hydrogens are shown. So the way that we take the hydrogens off when we're drawing carbons, we would not do that with other atoms. For example, draw you another structure here. Stick with our rings just because that's what we're doing. So if I drew that kind of a structure, notice that the oxygen still, one of them has a hydrogen, one of them doesn't. And the nitrogen has 2 hydrogens. Yeah. Yeah, good question. Because carbon is super predictable. And we have that, like the rule number 2 with the hydrogens, that only works because we always know that carbon has 4 bonds in those situations. Other atoms don't do that. Like oxygen usually has 2 bonds, but it can have 1, it can have 3. Same thing with nitrogen, it can have like 2 or 3 or 4. So it's not as predictable. So if we don't show the hydrogens, we don't actually know how many hydrogens. So when you write oxygens or nitrogens in a line structure or any other kind of atom, you always also still keep their hydrogens there. Hydrogens don't come off the way they do with carbon. All right, and that's line structures. So we're going to practice this. Do you have a question? Okay. We're going to practice this a little bit with one other concept, and that is isomers. Isomers are molecules that have the same molecular formula, like, you know, C something, H something, O whatever. But they are connected in a different way. So let me show you what I mean. I'll use models. I would have us all do this together, but I don't think we have time. So just do it as a demonstration. We can work on this more on Tuesday during our review session if you want. All right, so I've got 4 carbons here, and I'm going to connect them together with some bonds. All right, I'm just going to leave the hydrogens off for now because we know that hydrogens have to do what they have to do, right? So I've got this structure, and we could draw that as a line structure, just be like, right? The other thing about this is single bonds rotate. They can do that in real life too, just like in the models. So I could have made this like this, and I have the same molecule. Things changed. I mean, it looks different, but it's actually still the same molecule because everything's still connected in the same way. The first carbon is connected to the second one, which is connected to the third one, which is connected to the fourth one. Still connected in the same way. You know, I can twist that around however I want. But this molecule also has an isomer, a way of taking these same 4 carbons but connecting them in a different way and making a different structure that we cannot interconvert just by twisting. Anybody see how you do it? Yeah, exactly. So if I take this one off and put it here, I have a totally different molecule. It's connected in a different way. I can't make it go back to the other one unless I disconnect it again. And so that makes it an isomer. So let's draw those in a couple of different forms. So we've got the first one that we've drawn before. And we'll draw it in a line structure, and we'll also draw it in a condensed structure. And I'll keep the same shape with the condensed structure so that it is clear. And then the second one I drew in a line structure would look like that. In a condensed structure would be like this. And so the trickiest part of all of this is figuring out whether or not two structures are the same or are isomers. So let's look at some strategies we can use to figure that out. We'll leave the butane up there for now, and let's add one more carbon, which makes it a little bit trickier, and talk about the isomers of pentane. So pentane has the formula C5H12. And one isomer we can always draw relatively easily, which would just be the straight chain. And then your challenge is draw two more isomers of pentane. So draw two molecules in any form you want that have the same formula but are connected in a different way. Same formula, connected in a different way, and they still have to follow the rules, which means carbon still needs 4 bonds, hydrogen needs 1 bond. When you think you've got one, come up and draw it on the board here. We want to try to get as many different examples as we can so we can compare them and see which ones are the same and which ones are different. Anybody find one yet? I mean, we just learned this, so it doesn't, I'm not expecting you to like get them all right. The point is we want to look at some different ideas and structures and see what they look like and whether they're the same or not. So come on up and let's see what you got.
The number of hydrogens can change.
No. Well, the number of hydrogens on each carbon can change, yes. But the total number of hydrogens has to stay the same. Go for it. Yeah, go ahead. There's one more. All right, who else we got? Yes, go ahead. Grab Parker. There's some from the engineering. You don't have to put your name on them or anything. I'm just gonna make this a little darker so you can see. Nope. All right, that's a good set. Thank you very much, those of you who came up to draw. Anybody else have a great one they want to throw in? All right. So first question. So the questions we want to know is, of these structures, first of all, which ones are valid isomers, meaning which ones do have the same formula C5H12? And then second, which ones are the same or the same as ones we've already drawn? So I'm going to transfer these up on here so we have them on the notes. All right, so the far left, we've got one that looks kind of like this. Let me know if I'm not copying it right also. Then next to that one, we've got this one. Then the next one over is like this. And then the final one over here. So the first thing we want to know is which one of these are not C5H12? Which one of these do not have that molecular formula? So you see a couple. Yes. The one all the way to the left? Why?
Has 6 carbons.
Yeah, that one has 6 carbons. Did everybody see that? 1, 2, 3, 4, 5, 6. And if we can count up the hydrogens too, and we'd end up finding that this one is C6H14. So that one's got a different formula. So that one doesn't work as an isomer. What else? There's one more here that doesn't have the same molecular formula.
The other green one?
Why?
Am I right?
Are you?
I don't know.
You're not in your head. Why?
I don't know. I just.
Doesn't look right?
Yeah.
Well, you all have good chemical intuition because it's true. But that one is C5. That one does have 5 carbons. The problem is in the hydrogens. So let's actually look at count up all the hydrogens. So we've got 3 here, 1 here, 2 here, 2 there, and 2 there. So what does that add up to? 10, yeah. So this one is C5H10. If you think about that from the models, I already took it apart. If you try to close the ends on a model, that takes up holes that could otherwise be used for hydrogens, right? And we're going to talk about these types of structures called cycloalkanes later. But when you close that circle, you have to remove some hydrogens to make room for the closing of the circle for those extra connections. So that's why that one doesn't quite count. All right, so the other 2 here do have the correct formula. C5H12, C5H12. So that's your first step in checking if things are isomers. Check the formula first. If the formula matches, now comes the really hard part because we've got to think about these things in 3 dimensions and how they would rotate. So of those 2, are those 2 different structures from the first one we drew, meaning they're isomers, or is either of them the same as the first structure that we drew?
Same as.
Yep, exactly. So the 2 that are next to each other here are actually the same. This one and this one are the same. Because if you imagine kind of stretching that out or twisting it out, you get that same structure again. Those 2 structures only differ from rotation around a single bond. And so they're not isomers. Isomers have to actually be connected in a different way, not just differ by rotation. So those are not isomers. And that's one of the things that's tough about this. Is this idea of visualizing these things in 3 dimensions and thinking about what would this look like if this were to twist in this particular way. And that could be tough. So next week when you're doing the exam, I'll have the models here, and if you need to come build some stuff and check it out, you can do that. Yep.
Isn't it an isomer?
Because it's not connected differently. So each carbon is still connected to the others the same way. Yeah.
So how many other things are involved?
So this one is an isomer. And there is one more isomer of pentane, which looks like this. So the last thing is, how can you tell that those are isomers and the other ones aren't? One way is to build them, twist them around, and compare. But if you can't do that or you don't want to do that, you look at the way that they're connected, and one way that people have found is helpful is to think about the longest continuous chain. So how many carbons are connected in a row on each of these structures? Take a look at these. So the first two each have 5 carbons connected in a chain, one after the other. See that? This one also has 5 carbons connected in a chain, one after the other. See that too? Now let's look at the isomers. The isomers don't have 5 carbons connected in a chain. This one has 4, with then one extra one kind of coming off of it. So there's this discontinuity, this disconnection there. And then this one has 3 with 2 separate ones coming off of it. So that's one way to visualize it and say, okay, well, here's how we can tell that this one's different from this one, which is different from this one, is the way that they're connected. Yeah.
On the other one, the one in the middle.
Yeah.
No.
They're what?
The one you drew in the bottom right corner.
Yeah.
One of the carbon in the middle has no.
That's correct. So it's got 3 on each of the outsides and none in the middle. And actually, that's another way to tell isomers is to convert these to their condensed structure. So like you're saying, this one in a condensed structure kind of looks like this. And so immediately you could see that's the only structure here where there's a carbon with no hydrogens attached to it. So that tells you, oh yeah, this must be something different because this carbon has different numbers of hydrogen than the others. All right, so we're just about out of time, but I want to make sure you're prepared for this. So for homework and exam prep, see if you can find 5 isomers of hexane. Hexane is C6H14. And there are 5 different isomers. And see if you can find them without looking anything up. And it's not like you're going to turn this in anyway, so don't look anything up. Draw the structures, and either with yourself or ideally with other people as you're studying, see if you can convince yourself and each other about which ones are the same, which ones are different, and make sure that you can convince yourself or you understand why the 5 different ones are actually different from each other. Does that make sense? So 5 structures that are different from each other, but that all have that same formula. Yeah.
We did all of it.
We did not. All of the last one. So yeah, if you look at the objective for the exam, all but the last number on organic chemistry, which is about functional groups, all the other ones are included. So that's where we cut this off Tuesday. Yeah, we just looked at the yeah, we'll get it.
All right, see ya.
Yes, yeah, same thing like last time.